Okay, so let's continue. So the next item that we're going to discuss is the use of this hypothesis testing to aid statistical methods. Okay, so we have started already with this t-test. So what we're going to do is we continue on discussing what are the different hypothesis testing. For instance, the t-test, um, we use it to decide whether there's a statistical significant difference between the two mean values. So this is, we could say, the null hypothesis for the t-test. So it states that two sets of measurements come from populations with the same population mean. So we reject the null hypothesis if there is less than a p equals to 5% chance that the two sets of measurements come from populations with the same population mean. So we could say statistic gives us the probability that the observed difference between the two means arises from random measurements uncertainty. So here we're going to discuss two cases where we compare experimental mean with the true value, and then we compare two experimental means. And then we will going to do F test and Q test and G test as we go on. So F test, the same thing as the T test, but the way that we're going to look at F test is comparison of the precision of measurements. Q test and Grubbs test is in detection of these gross errors or outliers. Okay, so let's try to look at the first one. A sample was certified by NIST to contain 3.19 weight percent sulfur. So the measurements obtained using the sample are 3.29, 3.22, 3.30, and 3.23% sulfur. Does this agree with the reference? So this is now a comparison between experimental mean and the true mean. Okay, so we could use here confidence interval just to see if the set of values that we have is within the true value. So maybe we could start using here the 95% confidence interval. So if you remember from our previous example, this is the formula. X minus plus or minus T times S over N, square root of N. So if we're going to do this thing, the first thing that we're going to do is get the mean and standard deviation for this. So if I do a calculation of this, I'm going to get this value, and then plus or minus 3.182, okay, and the standard deviation of 0.04. Square root of 4. Now, where did I get the 0.04? 0.04 is the standard deviation when I set this, when I use these four values. Okay. Now, where did I get the 3.182? So if you're going to remember, we have the T table. So this is 19%. So we have there what? 3.182. So 3.182, so 1, 2, 3, 4. So this is 95% interval that we use. So 4 degrees of freedom will be 4 minus 1, so we use 3.182. Okay? So what's the value that we get? So you will have here 3.260 plus or minus 0.065. And this will become 3.95 to 3.325% weight. So what can we say? Okay, 3.19. It's just outside 3.915. So we could say here, at 95% confidence interval, we can conclude that there is less than a 5% chance that our value or our method agree with the known answer. Okay? So for you to agree, that number should be included here. But as you can see here, at 95%, it's not included. So that's an example on how we compare experimental mean with the true mean. Now let's go on another set of t-tests. So this time, this is comparing two experimental means. So the masses of gas isolated by Lord Rayleigh is given here. So as you could see here, this is the average for one set of experiment and its standard deviation. And this is the average of the another experiment and its standard deviation. So what are we going to do here? So there's a question here. The average mass of gas from the air in table 4-3 is x1, mean one is 2.31011 gram with a standard deviation of 0.000143 for n equals to 7 measurements. Now the mass of gas from the chemical sources is x2, 2.2947 gram with S2, 0.00138, N2 equals to 8 measurements. So what you're going to do here is you're going to calculate with the T. Okay? And the formula that you have here is this. T calculated is equals to the difference. Okay? X1 minus X2, the difference of the average absolute value over S pool times the square root of N1 times N2 over N1 plus N2. Now the question now here, how do we get the X pool? So there is a formula for this S pool. So this is just the full standard deviation. So if you're going to look at here, S pool is equals to the square root of standard deviation squared times N1 minus 1 plus standard deviation of the second one squared times N2 minus 1. And then you're going to divide it with N1 plus N2 minus 2. So I think this around here is the sum minus the degrees of number to give you the degrees of freedom. Now we can do this one here. So if we just replace whatever value that we have here. So S1 squared. So that's 0.000143. Okay. Times, what do we have? 7 minus 1. So that is equals to 6 plus 0.00138 squared times 8 minus 1, 7 divided by, what do we have here? 7 plus 8 minus 2, and then get the square root of everything. And this will give me, I get around 0.00102. Please check. in your calculation. Now, I'm going to use this one for here. So if I'm going to replace the value that I have here, so I have what? Absolute value difference of 2.31011 minus 2.29947, and then I divide it with 0.00102, and then replace it with 7 times 8 over 7 plus 8. And I'm going to get here the value of around 24. So that's the T calc. Now the question now is, how am I going to compare this value with the T value? So I get 20.2. So what's the number that I'm going to compare it in this table? In this T table. What number will I use? Okay, so to determine the number that I'll use, you just go back here. So 7 plus 8 will give you 15 minus 2, so that will give you around 13. That is the degrees of freedom. So all you need to do is maybe use the value in between these two. And you can choose whatever interval that you have here. So it is from what? Between 10 and 15 at 95%, it is from 2.131 and 2.228. So what can you say about that value? 2.228 to 2.131. Now, since the T calc is much higher than the T tab for table, so we could say they are significantly different. The two sets of means are significantly different. And what will tell us that is significantly different? Well, if you're going to plot the data, so the one set of data is here, and another set of data is here. So in one way or another, they cannot be the same. They're not even overlapping. So that's the interpretation on why they are significantly different. Okay, so if the T calculated value is much higher than the one that is the T table value, then there is a significant difference between the two. Okay? Or you can also do using the Excel, the calculation between the two. And if you're going to look at this, so this is the T stat that you have there. Whether you use t-test 2-cell assuming unequal variances or 2-cell assuming equal variances, so this is the value that you will get. Okay, and if you're going to look at the table, so you have this value and this value, and it still have a higher value that you have there compared to the one in the table. So in this case, they are really different. Okay, now there's another way to determine them, to compare the two sets of experiments, but this time you use the F-test. So F-test is different from the T-test. Okay, in such a way it determines precision. You can do T-test and F-test at the same time, but there is a condition when you do the F-test. In the F-test, the standard deviation that is larger, okay, I mean, you always have to assume that the first standard deviation is larger compared to the second standard deviation. In other words, you always put the larger number or the larger standard deviation in the numerator. And then you check and compare the calculated F with its critical value in the F-test table. So if it's larger than the critical value, so you could say the both methods are different. They're significantly different. If it's smaller, then they are not significantly different between two methods. So the one that you use in the F-test is only the standard deviation, unlike in the T-test. Okay. So if you're going to look at this, there's also a table that you have for this F-test. And what I want to do here is we're going to use the same set of data that we have in the previous problem. So we're going to use this value that we have here, 0.00138 and 0.00143. Okay, so how will I solve that thing? So I would just here f calc. So I'm going to put the one that is higher, okay, compared to the one that is lower. So I can put here the 0.00138, that's squared, and then 0.000143 squared. Okay, and then I get whatever value that that we have there. So in this case, this is what? 93.1. So what will I do? I need to get the f-top value. So if I'm going to f-top value, how will I going to look it here? So remember, one has 7 and the other one is 8. So in this case, this is the one that has the 8. This is the one that has the 7 measurements. So I subtract each one of them. I'll go to the one that has 7 and 6. So S1, I have here what? 7. And then I match it with the one that has the 6. So I end up, the f-top is 4.21. Are you clear on that? You're going to need this table if ever we do an exam. So if we're going to look at this here, f-top is different than f-top. It's so high. So there's a significant difference between the two. So it agrees with what the t-test shown. Okay? Now, the next set of things is finding the so-called outliers. So outliers are suspected gross errors. So it can either be too high or too low of number. So the classic way to determine the outliers or detection errors is by Q-test. So in the Q-test, you're going to find the Q value. Okay, so Q calculated or Q experimental. Wherein you're going to look at the questionable data and subtract it with the data, okay, that is closest to the questionable data. And then you divide it with the range. So the difference between the questionable data and the nearest data is gap. Okay, range is what? The highest, the difference between the highest and the lowest value. So you're just trying to get some sort of a gap over the range, and you can use here a decimal, an absolute value. Okay, so let's try to do this one. 19.5, 19.6, 19.4, 19.8, 20.1, 20.3, and 15.3. So please select, please use Q-test to decide whether 15.3 should be retained or rejected at 95% confidence level. So what do we do here? 15.3. So what's the closest that we have in 15.3? So 15.3, so the closest that you have is, anyone? 19 point. What do we have as the closest here? 15.3 minus 19.4, right? Over 20.3 minus 15.3. So what do you get? So this is 5. The one that you have here, since we get the absolute scale, so that's 15.3 minus 19.4. So that's 4.1. So 4.1 divided by 5, we have 0.82. So what are we going to do? We have to compare it with Q table. the one that tells us whether if this is an outlier or not. So again, just like before in the two t-test and f-test, if the q calculated is greater than the q table, then you're going to reject it. If it's not, then you're going to retain it. So let's see. How many observations do we have? 1, 2, 3, 4, 5, 6, 7. So if we're going to look at that 7, the Q value should be 0.51. Okay, so Q calculated is 0.82, much greater than 0.51. Then we could say we're going to reject that lowest number. So that is an outlier. Okay? So in all of the calculations that you have to compare the value that you calculate with a table that will tell you whether there's a significant difference or not. If the calculated value is higher than the one in the table, then there's a significant difference. For the Q test, if the Q experimental or calculated value is higher than the Q table, then you have to reject. If not, you're going to retain. Now, we can also put it here. So 90%, 0.51, 0.568, 99%. So we still reject it, because the value that you get is still higher. Now, the last part that we have for the experimental one, instead of the Q test, so the Q test, I learned it when I was a student. They have other tests that they use for outlier, and they call it the Grab's test. So here, the G calculated is obtained by getting the absolute value on the difference of the questionable value and the mean divided by the standard deviation. So it's just very straightforward. So let's try to do this one. So students dissolve zinc from a galvanized nail and measure the mass lost by the nail to tell how much of the nail was zinc. So here are the results: 10.2, 10.8, 11.6, 9.9, 9.4, 7.8, 10.0, 9.2, 11.3, 9.5, 10.6, and 11.6. So what you need to do is get that value and this. So what's the questionable that we have? 7.8. Now, if you're going to get the mean of this, you will get around 10.16. And then the corresponding standard deviation when you calculate this set of numbers around 1.11. And in that case, it will give you around 2.13 of G calculated. Now, how are we going to compare it? Number of observations. So how many do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you have there 2.28. And it is less than, okay, 2.13. So what do? We're going to retain this value because it's less than, the G calculated is less than the one that is G top. So this is all that we have for this week. I'm going to have a slide again, but this time all problem solving time. So please watch this video, okay, for this week. So thank you very much and see you on Wednesday to some of you.